We all know the famous image. A giant rocket breathes fire and smoke. It strains against gravity, slowly lifting itself toward the heavens. This powerful display is a perfect example of Newton's third law of motion. For every action, there is an equal and opposite reaction. To go up, the rocket must push something down. In this case, it pushes a massive plume of hot gas out of its engines. This simple, elegant principle has been the bedrock of space travel for nearly a century. We throw mass out the back to push our ships forward. It is the cosmic equivalent of a swimmer pushing against the water to propel themselves across a pool. This method, known as mass propulsion, is surprisingly versatile. While chemical rockets use controlled explosions, other designs are more subtle. Imagine a spacecraft harvesting dust from the moon or chipping off pieces of a nearby asteroid. A machine could grind it to powder, even ionize it, stripping electrons to make a charged gas. Then powerful electromagnetic fields hurl it into space at incredible speeds. The ship inches forward, pushed by the steady stream of tiny particles it ejects. Engineers have become masters at tuning this process. The core equation is thrust equals mass times speed. This means you have two knobs to turn. Eject a lot of mass slowly for power, or a tiny amount extremely fast for efficiency. It's always a trade-off between power and endurance. Air drags exhaust on Earth. In vacuum, nothing gets in the way. For a long time, we have thought of the vacuum in simple terms. We measure its quality by counting atoms in a volume. A good vacuum is simply empty space, a void. This picture may be profoundly misleading. A new perspective says vacuum is defined by properties. Think of space not as an empty box, but as a medium, a fabric with its own characteristics. One key characteristic, field conductivity. Imagine you're driving a car on a freshly paved superhighway. Smooth, slick, motion with minimal effort. Other times, a rough, muddy country road, sticky mud grabs the tires. Both can be empty of cars, yet their properties differ. Space is like this. Some regions are highway-like, others muddy. Strong vacuum, calm, conductive fields. Weak vacuum, unseen field tension and fluctuations. In a weaker vacuum, objects fight stickiness, quantum jitters that create hidden drag. That friction isn't atoms or air, but the structure of space-time itself. Moving through space is interacting with an invisible field. When a rocket throws shredded mass, the field sees the ship and the exhaust making a wake. Not a hard wall, but an increasingly sticky field as you near the speed of light. What if, instead of pushing harder through mud, we change how we touch the road itself? The quanta perspective flips the problem. What if we don't have to throw mass at all? What if, instead of fighting stickiness, we change our interaction with the field? Imagine a car stuck in mud. Press a button. The mud freezes into a smooth, icy surface. No need to spin wheels harder. It simply glides. That's the core of massless propulsion. It's not about pushing harder, it's about making the road smoother. Apply energy in a specific, coherent way and locally alter the vacuum. Create a bubble of strong, conductive space-time. Inside, the ship's interaction is neutralized. Quantum drag fades. Instead of pushing against space, it glides along field pathways. No mass ejection. A key idea is a proposed 4-to-1 energy-to-mass ratio. It's not a proven law. It's a theoretical claim. For each unit of mass, 4 units of specific energy effectively hide that mass from the field. That energy isn't thrust. It's tuning the local field conductivity. Like tuning a radio, you cancel static so motion flows effortlessly. Efficiency gets redefined. Sustain the neutral state. You aren't throwing mass away. You persuade the universe to let you pass. While this sounds like science fiction, consider a black hole. Gravity there warps space-time into a one-way street. Nothing, not even light, escapes. Nature already manipulates space-time. Doing it ourselves may simply be very hard. Our rockets and black holes follow the same laws, yet act differently. Our understanding is incomplete. The Higgs field permeates space and gives particles mass. If mass is an interaction, perhaps interaction and inertia can be changed. Shredding and ejecting mass has limits. Massless propulsion could sidestep them. If we make the vacuum superconductive to motion, the solar system and the stars could open. We stand at a crossroads. Proven mass propulsion, or a quieter path through conductive space-time. The future may be mastering the fabric of the universe, not throwing rocks out the back.